Good morning. Well, I would like to thank the people who have invited me to participate in this really great meeting. Marta Losada and Diego Restrepo and the rest of the organizers, because it's really a beautiful meeting. In the first run of LHC, we have seen a historical success, which has been the discovery of the Higgs boson, of course. But all of us hope that in the second round we will see a similar success, which will be the discovery of beyond standard model physics. In fact, this is the second main goal of LHC. It is true that the first run of LHC has not produced any real hint or any serious hint of BSM, of beyond the standard model physics. Although there was a reasonable hope to find it, because the Higgs sector, which has been a new and the last standard model sector, which has been discovered, somehow represents a terra incognita, some new territory where we can find some surprises. But we haven't found any for the moment. It works quite well. Also, there was an expectation in this sense, because the main arguments, or one of the main arguments to expect physics beyond the standard model at the reach of LHC is the hierarchy problem, or the naturalness arguments based on the hierarchy problem. And these are based on the process of electroweak symmetry breaking, which is precisely the sector which has been discovered at LHC. So it was natural to find, or to expect to find, some signs of new physics in this new arena, but we haven't found any. So unfortunately, or maybe fortunately, I don't know, Higgs physics seems to be in a great agreement with standard model predictions. All of you have seen plots of this kind many times, also in this conference. So it seems that the Higgs boson really looks like the standard model Higgs boson. And by the way, LHC has not only discovered a new, or the Higgs boson, which is of course a major discovery, but also new interactions, new forces, the Yukawa interactions, which is also another major discovery. But everything seems to work perfectly well in the standard model scheme. So if we have some hope to find new physics, that new physics should be now hidden within the error bars of these wonderful plots. Of course, somehow this is wishful thinking, but it's also true that although the LHC results are very impressive, the error bars are still sizable, and there is room there for new physics. Also, some very important properties of the Higgs boson have not been yet checked. For instance, the decay into muons, or even more important, the self-coupling of the Higgs. So, well, we have also seen in the first run that not only Higgs physics is in great agreement with the standard model, but everything that has been seen. So the results show an impressive agreement with the standard model in all the many channels that have been analyzed by both ATLAS and CMS. These summary plots represent the perfect or almost perfect agreement within the error bars between theory and experiment. There are just a few, what is this? A few hints or slight of order 2 sigma deviations which have been left after run 1. For instance, a 2.6 sigma excess in the production of dileptons plus jets plus missing energy. This has been just reported by CMS, and probably ATLAS will give a similar report in the next months, I suppose. Also, there is a 2.5 sigma signal for the Higgs going to mu tau, which has been also reported by CMS, and a 2 sigma excess in WW production reported by both ATLAS and CMS, and some other slight hints. Well, of course, it will be really exciting if these hints are confirmed in the new run. Actually, already people have imagined explanations for these deviations based on beyond the standard model physics, in particular involving supersymmetric states, quarks and leptons. But of course, one has to be extremely cautious, because there are so many channels that have been analyzed, so many analyses by ATLAS and CMS, that it's not strange that somewhere there appears some small deviation, a 2 sigma deviation. Even statistically, you can expect that. Also, this kind of apparent signals could be caused sometimes by a not sufficiently precise estimation of the background. The control of the background is really crucial to detect beyond the standard model physics. And of course, the QCD people are doing a great job in this sense, but we really need it, because otherwise it's impossible to detect beyond the standard model physics. As an example of this, the WWXS that was reported first as a deviation with respect to the next to leading order theoretical prediction by ATLAS and also then by CMS. Then, after, in this paper, they have incorporated the next to leading order correction, the theoretical prediction has increased, and now the signal has become much less impressive. So this can be also the story of other apparent beyond the standard model signals. The control of the background is really very important. Now, all this absence of hints of beyond the standard model physics in the first run of LHC has produced, in at least part of the community, the sense that there is a tension between the experimental results and the natural arguments which are behind the hierarchy problem. How strong is this tension? Well, that depends on the people you are talking to. But this is a quite general sense at the moment. So maybe we can recall once more the old hierarchy problem, which is very easy, in fact. You just compute the quadratic contributions to the Higgs mass parameter with a cutoff. They have this form. The most important contribution is proportional to the top Yukawa coupling, and has this value. And if you demand that this contribution is not much larger than the mass parameter itself, say 10 times larger, then you find a lower bound on the cutoff, which is, for the Higgs mass, for the actual Higgs mass, is 1.5 TeV. And this argument is really the main reason to expect beyond the standard model physics at the reach of LHC, because there are other reasons to believe that there is beyond the standard model physics, for instance, dark matter. But this is the reason, or the main reason to expect it there, at the reach of LHC. Well, of course, the naturalness criterion associated to the hierarchy problem is, we have to admit, which is quite imprecise. Maybe it's too naive. Maybe it's a misconception. Maybe it's wrong. But since it is, or it has been, our main argument to expect beyond the standard model physics, we can ask to which extent the LHC results so far are in tension with this naive, maybe naive hierarchy problem argument. And in this sense, notice that the LHC has explored a lot of physics up to 1.5 TeV, but not all the physics up to 1.5 TeV. In particular, the hierarchy problem, or the strongest bound coming from the hierarchy problem, applies to the beyond the standard model physics associated to the top, because it's the top, the particle which is producing the main contribution to the Higgs mass. Therefore, this bound applies to the, say, top partners, or the associated to top physics, which is going to solve the hierarchy problem. But you can see that even if, in fact, there are top partners below 1.5 TeV, for instance, at 1 TeV, they could have easily escaped the LHC in the first run. This is why LHC has not explored all the physics up to 1.5 TeV. For example, if the beyond the standard model physics is supersymmetry, then the top partners are the stops, are the ones that cure the hierarchy problem, okay? But then the present upper bound on the stops is 700 GeV, which is below 1.5 GeV. In fact, it can be smaller depending on the topologies on which the top decays. So this will be okay. So maybe it is a bit too soon to give up. It's a bit too soon to say that the LHC has disproved the hierarchy problem argument to expect new physics. So we have seen that it could even happen that the naturalness criterion works, it's sound, but the beyond the standard model physics is just above the reach of the rank 2 of LHC. This would be really a very unfortunate situation, but these things have passed, has happened in the past. So if we are not very lucky, this could happen again in the rank 2. We hope it will not happen. Notice also that the naturalness bounds, which are quite imprecise in this naive formulation, become more precise when they are analyzed for concrete beyond the standard model scenarios, because then you can evaluate the contributions to the Higgs mass parameter in terms of the initial parameters of your model and the contribution through radiative corrections to the Higgs mass parameter. We will see an example of that later. Well, it's interesting to mention that there are other, though not that strong, there are other reasons to expect beyond the standard model physics at the TeV scale. The most important one probably is dark matter. Dark matter, of course, is an extremely important issue. But if dark matter is a WIMP, and it could be a natural candidate for dark matter, because it has the good coupling and the good mass to behave as a dark matter particle, then we could expect these WIMPs to appear at the LHC, because their masses will be between 10 GeV and 1 TeV, more or less. Also, if the discrepancy, the present discrepancy about G minus 2 of the muon is real, then this will be a signal of new physics, most probably at around the corner, at the TeV scale. So there are two main possibilities. The first one is that the naturalness criteria don't apply, because they are maybe misconception about the hierarchy problem. Maybe there is a landscape, and we are just playing something that has no sense, because the values of the value in particular of the Higgs mass and the scale of the electroweak interactions is fixed by other facts, in particular by the landscape. There are many universes. And maybe there are other alternatives to the hierarchy problem which do not rely on beyond the standard model physics. This is a possibility. But other possibility is that the naive naturalness arguments apply. And in that case, we can expect new physics around the TeV scale. Possibly, if we are lucky, at the LHC reach. For instance, supersymmetry, composite Higgs, extra dimensions, we don't know. So, of course, at the moment, we don't know which way has been chosen by nature. But it seems reasonable to explore both possibilities, but definitely it seems reasonable to explore this possibility, that the naturalness arguments apply, and we have beyond the standard model physics to discover. So let us assume for the rest of the talk that the naturalness arguments apply, and we expect this new physics. Now, which kind of new physics? There are many possibilities. Probably the most interesting ones, the best motivated ones, are these: supersymmetry, composite Higgses, warped extra dimensions. These possibilities have nice theoretical motivations. And of course, it is a matter of taste which would you prefer. No? Now, in fact, these are not models. These are frameworks which can have many models inside. For instance, in supersymmetry, you have the minimal extension of the standard model, which is the MSSM. You have the next to minimal, NMSSM, low scale SUSY breaking, R parity violation SUSY, many possibilities here. Even inside the minimal extension of the SUSY, of the standard model, you have the constrained MSSM, the non-universal Higgs masses model, the gauge-mediated MSSM, string-spied MSSM, many models. Now, in the search of new physics in the LHC, it can happen that beside this new physics, which is related, at least in this motivation, to the hierarchy problem, there could appear other kinds of new physics. And the most important examples are these ones. Dark matter. If we are lucky, LHC will discover dark matter. Of course, dark matter is an extremely strong, is the strongest argument to believe that there is beyond the standard model physics. But it is not clear that that new physics is going to appear at the LHC. If we are lucky, we will see it. And another one is flavor physics. Maybe we are lucky and we find hints of the physics which is behind flavor at LHC. This has been discussed in the talks by John Ellis, Alejandro Ibarra, and Josinier in the past days. In fact, there are other models of beyond the standard model that could be found at the LHC, and in fact, they are being explored at the moment. For instance, set primes, extended Higgs sectors, for instance, two Higgs doublet models with singlets and so on, universal star dimensions, etc. Now, there are two main strategies to search for beyond the standard model physics. As always, direct searches and indirect searches. Direct searches means to try to produce directly the new particles associated to the new physics, to see new particles and see new processes. And the other case, what you see or what you will see are fingerprints in the effective theory. If you make precision, or you determine with precision some processes or some observables in just playing with standard model states, you can find maybe hints of higher order operators which are signals of new physics. In fact, in the last 2 years, there has been a lot of work in this direction. Now, which one of these two strategies is the most efficient one? Well, in fact, this depends on what kind of new physics is around the corner, if it is around the corner. Depending on what is the new physics, depending on what is the beyond the standard model physics, then one or the other strategy can be the most efficient one. And we will see a couple of examples of this. So, of course, the most reasonable thing is to explore both avenues, and we will see where the new physics appears. Now, coming back to the beyond the standard model physics, which is related to the hierarchy problem, so these possibilities, supersymmetry, composite Higgs, warp extra dimensions, it is true that these models or these frameworks are beautiful. For instance, supersymmetry, I think, is a very beautiful framework and very well motivated. But it's also true that all of them, when you go to the details, they look much uglier, or at least uglier. So maybe this is a bad signal, that they look uglier. Or maybe it's that we are not ingenious enough to devise good beyond the standard model, or beyond the standard model physics, beyond the standard model models. We'll see. Now, I will focus in the rest of the talk mainly on supersymmetry, which is part of the title of the talk. But just a few words about composite Higgs. The present composite Higgs models normally incorporate the Higgs as the pseudo-Goldstone boson or some symmetry which is spontaneously broken. In this way, you can make the Higgs boson naturally lighter than the other states which live in the scale where these interactions are strong. This is similar to the way in which the pion is much lighter than the other strong resonances. So this is an interesting possibility, because in this case, the hierarchy problem is solved because at this scale, at this TeV scale, in fact, you see that the Higgs is not a scalar, it's a composite of fermions, and you don't get any more large quadratic contributions to the mass. However, there are problems. In particular, in order to reproduce the top mass, then you require couplings of the top to heavy composite fermions, which will be the top partners with masses of order 1 TeV. So you have to write terms in the Lagrangian of these kinds, where these capital letters in red are the top partners. So this produces that the physical top is really a partially composed particle. But all this game produces modified Higgs couplings to the standard model particles. So in fact, I think that for composite Higgs models, to look for signals of beyond the standard model physics in the effective theory associated to the Higgs is the natural arena to find these signals, because you expect really modified couplings of the Higgs. So I think this is natural. So in this case, probably the most efficient way to find or to look for this new physics is to look at these precision observables. Now, what about SUSY? Well, everybody knows the motivations of supersymmetry. In particular, it is a beautiful symmetry, strongly suggested by, or even demanded by string theories. It offers a very elegant solution to the hierarchy problem. Everything is great. Also, it has some extra bonus. In particular, the Higgs looks fundamental, the Higgs that we are seeing, and precisely supersymmetry predicts, or the MSSM, for instance, that the Higgs is a fundamental particle. More important, the Higgs has a mass, 125 GeV, which is below 135 GeV, and this is the upper bound for the Higgs mass in the MSSM. And this is not trivial at all. The Higgs could have been 200 GeV or 300 GeV, and in fact, this will be better for just a standard model, because in that case, the Higgs potential will be perfectly stable. But no, it is in this region below 135 GeV. This is a success of supersymmetry. Also, it implements in a very natural way the electron-wave breaking. The fact that the SU2 cross U1 part of the theory is spontaneously broken comes in a natural way. It has very good candidates for dark matter, WIMPs. Normally, it is the lightest supersymmetric particle, which usually is a neutralino. And also, it shows a beautiful unification of the gauge couplings of SU3 cross U2 cross U1. Everything is nice, but first, a Higgs of 125 GeV is okay for SUSY because it's below the bound, but it's a bit too heavy for naive supersymmetric expectations. In particular, this kind of mass makes at least the minimal version of the supersymmetric standard model, the MSSM, makes it somewhat fine-tuned. So this is not nice. Also, and even more important, we have not seen any sign of SUSY in the first run of LHC. Of course, this is shared by all the models of beyond the standard model physics. And finally, these two facts together imply that the supersymmetric particles must be around or above, roughly speaking, 1 TeV. And this is not very good because this means, as I said, that the MSSM, at least, is fine-tuned to some extent. Fine-tuned in order to get or to achieve the correct electroweak scale. I think this problem also happens in all scenarios of beyond the standard model physics. Now, I think that in contrast to what happened for composite Higgs models, for supersymmetry, typically direct searches are more efficient to find supersymmetry than looking for fingerprints in the effective field theory in general. And this is because SUSY has a symmetry which is R parity, which makes that in all diagrams that you can draw with just standard model particles as external legs necessarily must have a loop, because all the vertices have always two supersymmetric particles. So automatically, the terms that appear in the effective Lagrangian, for instance, an operator of dimension 6, h to 6, okay, comes with this additional suppression, 4 pi to square. So in a very natural way, supersymmetry is decoupled from low energy physics. In part, this is not nice because it makes more difficult to find supersymmetry through deviations on these higher order operators. But on the other hand, it's good because we haven't seen any sign so far. But this is the situation anyhow. Okay, now what about direct supersymmetry, direct production of supersymmetry at LSE? Now, the highest cross-section for supersymmetry production are normally gluino and squark production in pairs. This is logical because we have a hadron collider. This is seen in this plot. These are the Q-bar squark gluino, squark, and gluino production rates in the first run of LSE. Now, what are the typical supersymmetric signals? Well, these two particles, the gluino and the squark, decay along long cascades normally with diverse topology. So each cascade always gives at the end the lightest supersymmetric particle, which, because precisely of R parity, does not decay anymore. So you always have normally at least two jets, one for each cascade, and also you have missing energy because of this lightest supersymmetric particle, with or without leptons. Both cases are interesting. So the most typical SUSY signals are jets with high PT, with missing energy, and with a diverse number of leptons. And this is the thing that have been searched intensely in the first round. Now, a problem is that it is not easy, or it is not straightforward to translate the results on this type of signals, to translate them into bounds in the MSSM parameter space, because the MSSM has around 100 parameters. So this is really crazy, but it's what we have. Now, most of these parameters are related to the unknown mechanism of supersymmetry breaking. That's the problem, because otherwise supersymmetry doesn't add essentially any other parameter to the standard model. Now, here there are then two main strategies. One is to translate the LSE results into constraints on representative, on typical or well-motivated supersymmetric models. For instance, the constraint MSSM, non-universal Higgs masses, non-universal Gino masses, and so on. Other strategy is to use clever simplified models to express the bounds. In a simplified model, you just put all the masses of all the particles to very high values, so only you play with very few particles, with very few masses, very few couplings, and you put quite concrete constraints. Then, when analyzing a particular scenario, what you have to do is to use the simplified models that mimic the physics of this model in each region of the parameter space. So it is true that simplified models are useful tools to explore the phenomenology of supersymmetry. However, one has to be careful when interpreting the results that the experimentalists give, because normally they use, or many times they use simplified models, and you have to read the small letters, otherwise you can imagine things which are not true. For instance, this is the plot for exclusion of the mass of the lightest chargino. Yes, the lightest chargino. This brown region is the exclusion region from first run, and this is the expectations for the second run. So this is very, very impressive, because you will get bounds of around 1 TeV, lower bounds of around 1 TeV for the chargino. This is very impressive, but it has been obtained under some assumptions. In particular, that the mass of the latest chargino is degenerate with the mass of the second neutralino, and that the decay of the second neutralino is through a set, and the decay of the latest chargino is through a W. This happens sometimes. For instance, when the latest supersymmetric particle is a Bino and the second one are mostly Winos, this is normally the case, but in many other cases it's not the case. For instance, if the second supersymmetric particle is a Higgsino, typically decays through a Higgs, and then you see nothing, so, or very, very little. So you have to take with care these plots. Well, okay. Now, on the other side, I said that it is also usual to translate the bounds into constraints in the parameter space of representative models. And the most representative one, or the most studied one, has been the constraint MSSM, because it's the simplest one, and it gives you a flavor of what is going on. In the constraint MSSM, you simplified all these parameters to just 4 or 5 parameters, which are defined at the scale of the unification scale. Then for this constraint MSSM, the typical spectrum has this form. The gluino has a mass of the order of the squarce masses, larger than the leptons, and the gluino is larger than is heavier than the charginos, which are similar or larger, heavier than the neutralinos. And the lightest neutralino normally is the lightest supersymmetric particle. Now, these are the constraints, in this case from Atlas, on the CMSSM in the M0, M1/2 plane, which are the universal scalar mass. In the MSSM, in the constraint MSSM, you assume that all the scalars have the same mass at high energy, at mx. And all the Giginos have the same mass at mx, which is m1/2. So you can draw limits on this plane. So you see that, roughly speaking, for the constraint MSSM, the mass of the squarks, which means the mass of the squarks of the first and second generations, must be larger than, this is a bit too much, what 2 TeV, I think it's 1.7 TeV, something like that. And the gluino mass is 1.2, 1.3 TeV. These are the lower bounds on these masses. Besides, the fact that the Higgs mass is quite large for supersymmetric requirements means that the stops must be heavy, because the three-level Higgs mass in the MSSM coincides with the set mass for moderately or large tangent beta. If not, it's even smaller. Then you need radiative corrections to raise the Higgs mass to the observed value. And the radiative corrections are proportional to the stop masses. So you need heavy stops. Well, heavy around at least 1 TeV, 1.5 TeV. And all this means that the CMSSM is in trouble. Not in trouble, but because it has been disproved by the experiment, but because these large masses mean that the model is fine-tuned. It's fine-tuned at about 1% or even more fine-tuned. And in fact, we cannot forget about the fine-tuning problem, because the main motivation to introduce supersymmetry, at least in a phenomenological way, has been to avoid or to cure the hierarchy problem, which is a fine-tuning problem of the standard model. Of course, the hierarchy problem is a much more severe naturalness problem than this naturalness problem of the MSSM, of supersymmetry. But in anyhow, you are assuming that naturalness arguments apply. So this is a problem. For instance, this is a Bayesian study of the parameter space of the MSSM, and you see that most of the probability is for quite heavy masses, for the gluino and for the squarks. So in fact, if we are unlucky, this will mean not only that the CMSSM is fine-tuned, but also that if nature is really the CMSSM, then there is a chance that we will never see it at LHC. So this will be really bad luck. On the other hand, the enormous universality assumed for the CMSSM is not really neither a theoretical or a phenomenological requirement. Because partially it is, because we need universality between the supersymmetric particles of the same species for the first two generations, otherwise we will have important flavor violation processes which had already been seen. So in part, we need universality, but not this enormous amount of universality that CMSSM has, and which was assumed just for simplicity. So going beyond the CMSSM is very plausible. And since we are saying that fine-tuning seems to be, at the moment, the main problem with supersymmetry, a reasonable guide, when we go beyond the CMSSM, in this case, because the CMSSM is quite fine-tuned, a reasonable guide is to look for supersymmetric scenarios which have as little fine-tuning as possible. And this kind of scenarios have been named natural SUSY. So a natural SUSY scenario is an MSSM as natural or as less fine-tuned as possible. In fact, the idea is not new. It has been worked in this line without this name of natural SUSY since many years ago. But the idea has been renewed, especially after the paper of these people, Papucci et al. They simply took the effective standard model coming from supersymmetry. They consider the Higgs mass parameter, which in supersymmetry for large tangent beta, which you need moderately, at least moderately large tangent beta in order to have the correct Higgs mass, has this expression. It's a sum of the mu parameter plus the soft parameter associated to the HU doublet. Then you can write at leading log the radiative contributions to this MHU parameter. They depend on the various soft parameters of the theory. The stop masses, in particular the left and the right stop masses, also the A parameter, and have this form at leading log. So studying these expressions, by the way, also the gluino does not appear here, but the gluino is the main contribution to the stop mass. So at two loops, there are an important contribution of the gluino to the MHU mass term. So demanding that these contributions are not very large, not larger than 10 times the mass parameter itself, you find that the stop should be light, say below 1 TeV. Gluino should be not too heavy, below 2 TeV, and you expect, or you will expect, quite light Higksinos, of around 500 GeV or less. This is for 10% fine-tuning. However, these standard, or somehow standard or popular arguments are a bit too simplistic. First of all, because the one loop leading log approximation is not accurate enough, because you are running from a very high scale to a low scale, and you have to do the running correctly, not approximated with the leading log approximation. Also, the physical square gluino Higgsino masses that they used are not the initial parameters of the model. These are consequences of the initial parameters, which are the values of the soft terms at a high scale. So one should evaluate the cancellation required to get the correct Higgs mass between the initial parameters of the theory. And this is a bit complicated because there is not a one-to-one correspondence between the initial parameters and the physical masses, but it can be done. And one important conclusion is that, for instance, one of the typical conclusions of natural SUSY, which is that stops should be light, not necessarily. Because, for instance, if you start with a theory in which the scalar masses are degenerate, are universal, which is a perfectly plausible possibility, then it happens, it's a coincidence, but it happens. You don't have to force anything, that the contributions to the Higgs mass parameter coming from the Higgs mass parameter itself and from the two states of the stops, they cancel almost exactly, and at the end you find that the contribution to the Higgs mass coming from the stops, coming from the mass of the stops, which at high energy is degenerated with the other scalar masses, is extremely small, is very small. So you can raise this mass, this universal scalar mass, without paying a fine-tuning price. However, the stop mass at low energy does not present any cancellation. It has a large dependence on the initial scalar mass. So if you raise the initial universal scalar mass, you raise the stop masses at low energy, but you don't raise the Higgs mass parameter at low energy. So if the stops are heavy because M0 is large, then there is no fine-tuning price with that. If the stops are heavy because the gluino is heavy, then you have a fine-tuning price. This is a clear counter example of the popular supersymmetry requirements. This for the stops. Now, for the gluino, it happens that the gluino bounds normally are both stronger than the stop ones and more robust, because there you don't have this fortunate cancellation between contributions. Though that depends on the model. Maybe there are models which have not been explored yet, which present accidental or maybe non-accidental contribution, cancellation of the contributions of the gluino, for instance, against the contribution from the wino, which have opposite sign. That could happen. But so far, we have not seen it. However, since the contribution of the gluino is a two-loop effect, it has a very strong dependence on the length of the running between the high scale and the low energy scale. The larger the running, the most important the effect, because it goes with the logarithm to the square, essentially. So it happens that when you decrease the high energy scale, and this could happen, for instance, for gauge mediation models, which can have a different scale, which is not a unification scale, then the naturalness bound on the gluino becomes much weaker. On the other hand, the bounds on the Higgs are the most model-independent ones, are extremely stable against changes in the framework. Because the running of the mu is almost doesn't run, and the running does not depend on the other parameters. So since the mass of the Higgs is related to the mu parameter, the naturalness bounds on the Higgs are very stable. Now, this is a table with some bounds obtained, in this case not for the constrained MSSM, but for the unconstrained MSSM. The unconstrained MSSM is, well, this is essentially is like the phenomenological MSSM, which is the PMSSM, which maybe you have heard other times. It's simply an MSSM in which all the parameters, you assume no correlations between them, except the fact that they have to be consistent with, for instance, the flavor modulation requirements. But apart from that, you assume that they are uncorrelated in principle. You assume no correlation in principle between them. So in this case, you don't have this focus point solution that I mentioned before, this solution in which the contribution of the stops is cancelled automatically or essentially cancelled. You don't have this cancellation because in this case, you are not assuming a universal scalar mass for the parameters, for the stops and for the Higgs, for the HU soft mass. But even though this is like this, the bounds on the stop masses are not that severe. You can see that if the high energy scale is, the unification scale is 1.6 TeV, and if it is smaller, then the bound is also less and less severe. For the gluinos, the bound is very important because a bound of 1.4 TeV for the gluino is much stronger for experimental purposes, is much stronger than this bound for the stops because it's much more difficult to find the stops than to find the gluinos. So this is a very strong bound. However, as soon as you decrease the high energy scale, this bound becomes less severe. If you go to scales of order 10 to the 4 JV, which are the typical scales of low supersymmetry breaking models, you find that the bounds on the gluino mass are not important. And also you can see here that the bounds on the Higgs are very stable. So conclusions, it is true that the run 1 of LHC has not offered any serious hint of beyond the standard model physics. And the results create a slight tension between the naturalness arguments and the experimental results. However, the motivation to search for beyond the standard model physics at LHC remains intact. And it is clearly too soon to claim that LHC results are in conflict with the naturalness argument. We will see in the second round what happens. Also, there are, in fact, well-motivated candidates for beyond the standard model physics, in particular, beyond the standard model physics that will cure the hierarchy problem, like supersymmetric composite Higgs models, extra dimensions. Supersymmetry, in particular, is in good shape, although it's somewhat fine-tuned. How much is it fine-tuned? That depends on the model. For instance, if it is the natural SUSY version of supersymmetry, then the fine-tuning is around 1% or even less. This is the situation at the moment. If SUSY is not found at the second run, then this fine-tuning will become more and more severe. This is clear. A conclusion related in particular to the natural SUSY scenario is that I think there is no solid reason really based on naturalness to expect necessarily light stops, in particular lighter than the gluino. There are scenarios in which the stops can be heavy. And finally, if the natural arguments are sound and supersymmetry is really there, then we could be about seeing supersymmetry in the second round of LHC. Thank you.
Thanks. Do we have questions or comments?
Do you think there could be a possibility of connecting the ultraviolet problem with the natural problem that you're talking about here?
Say it again, please.
The possible connection between the ultraviolet problem. That's why the quantum corrections of the fields do not vanish, and the natural problem. So there are two natural problems that are fundamental in physical theory and theoretical physics, and there is no solutions yet.
I don't really understand your question. You're saying that maybe...
There is a natural problem here that you have been talking about.
Yes.
And there is a problem of the ultraviolet cosmological constant.
Yeah. Cosmological constant.
That is
well,
120.
You're related now both.
I'm asking you if you could comment if there is any possibility of those two having the same solution?
Well, as you know, supersymmetric scenarios have naturally a smaller cosmological constant than the standard model ones. Yeah, but still is many orders of magnitude what we are saying.
120.
Yeah, exactly. So I don't think at least phenomenological supersymmetry is gonna, at the moment, is adding any new insight about the cosmological constant problem. I don't think so, really. This is clearly a very deep problem, which I think is not addressed by supersymmetry, at least by phenomenological supersymmetry.
But outside supersymmetry, then?
Outside supersymmetry? Well, I know very few models that can explain the value of the dark energy density. Apart from the popular ones based on the landscape, which will give you a reason. But apart from that, of course, there must be models in the market, but I don't think there is a convincing, serious theoretical candidate to solve the cosmological constant problem. I don't know.
Any more questions or comments? Just okay.
The case with asymmetry, without asymmetry, is an important case, and in fact, the collaborations, at least Atlas, has a group dedicated to this possibility. Of course, the signals are completely different. Typically, you don't have to have missing energy. This is the most important difference, because now, like the supersymmetric particle, decays. On the other hand, since you typically can have long-lived particles, you can have displaced vertices. And this is the way they are looking for parity variation signals. So far, unsuccessfully, but that could be an interesting possibility. I haven't mentioned particular scenarios, but parity variation ones are perfectly possible, because in fact, parity is something which is not, although it's asymmetry, it has been put by hand to solve a problem. So it's part of the uglier facts of supersymmetry, because it's something you put by hand to avoid proton decay. So it could happen that, in fact, you have a parity violation. In fact, maybe this is the most natural situation. But you have to, the violation cannot be very large because you can have problems, or it cannot be complete because you will have proton decay. But of course, this is being studied.
So you say that we shouldn't expect light stops because if you assume that they generate at the high scale, we have this cancellation that happens through the running, right?
It could happen. It could happen.
It could happen, right? So how degenerate must they be? How much space have we got? Can one be like one of the parameters be twice as much as the other? I mean, how exact must these parameters be such that the cancellation allows us to say we cannot have light stops?
Well, the problem with the stops is that if you have very light stops, in principle, this is not harmful, of course, for the electroweak breaking process. This is clear. However, it has a problem. The problem is that stops are related to the radiative corrections to raise the Higgs mass, to reconcile it with the experimental value. So if the stops are light, in fact, the solution can be more fine-tuned than if they are heavier. Because if they are light, you need a mixing between stops, which is related to the A parameter, which is quite precisely around the maximal value. And this is by itself a fine-tuning. So if you don't want that fine-tuning, you better have heavier stops. And in the case, in the table I showed, in fact, this is not a focus point situation, and still you can see that the stops can be perfectly well 1.6 TeV. Well, perfectly well. These bounds have been obtained for a fine-tuning of 1%. And this is a substantial fine-tuning, okay? But if you put here 10, you have to rescale these things, scale these things with the square root of delta. So if delta is 10, then you have to divide by 3 these bounds. So you will find stops of around 500, 600 GeV. But this is in a situation without focus point. If you have focus point, they can be much larger. They can be much heavier. They can be 2 TeV, 3 TeV without any problem. If they are massive, because the universal scalar mass is large, in that case. Because this is the parameter that you can move without paying a fine-tuning price. Okay? And also in this case, you can see that if the high energy scale is not mx, but is smaller, then this bound increases. So what I think is that there is no special reason to expect light stops, but they could be light. But funnily, very light stops, I think, are fine-tuned, which is because of this other problem of the Higgs mass.
So I certainly agree with your point that fine-tuning needs to be looked at in the right way, and that one should think in terms of fine-tuning of the original input parameters, not of physical masses. But I think fine-tuning is really a very sort of slippery criterion. So perhaps overall I would assign it even less weight than what you do. I mean, as far as the PMSSM is concerned, I think it's a shame to throw away the possibility of extrapolating up to very high energies. And we have this incredible piece of evidence in favor of that, which is the value of sine squared theta, which agrees at the sort of 1% level with a naive supersymmetric extrapolation. And in vast swathes of the PMSSM parameter space, you just cannot extrapolate up to high energies. So, I mean, maybe one should look at sort of restrictions on the PMSSM that do permit an extrapolation, although not necessarily to universal soft supersymmetry breaking masses. And then perhaps just a final comment, if I may, on this issue of the cosmological constant. Of course, supersymmetry does not solve the problem. On the other hand, I think it could be an element in the solution. After all, in supersymmetry, you get rid of the quartic divergences, you can get some control over quadratic divergences, which of course is not a complete solution to the problem, but it may be part of the solution.
I agree with you, only that if you are, for instance, in a scenario like case mediation, for instance, with a messenger scale, which is an intermediate scale, 10 to the 10 GeV or whatever, provided the soft masses of for the light particles are order 1 TeV, you will still recover the grand unification success of supersymmetry. So it's, you don't need to have the initial values at mx in order to have this, to preserve this beautiful success of supersymmetry.
Last question, you want? Okay. Any further questions or comments? Okay, if not, let's thank Alberto again. And
good morning, everybody. So first, I would like to thank to give me the opportunity to come here and present the results. So although there was a very nice summary before my talk, and it gives all the summary and the conclusions, and we all know about that. There's no hint of new physics beyond to standard model. And so I would be just presenting the results. Is it? Hello? Yep. Okay. If you can just like here. I can. Okay, so I'm just telling that. So I would be presenting the results, which and as you expected, a lot of the results are almost the negative suches, so you won't get anything. And but I would be presenting the limits plots. Okay, so by the way, I'm from California State University, and I'm working at Atlas experiment. So as it was described many times in this meeting itself, so the standard model is a very successful theory, and it describes the experimental data very well. And with the Higgs, with the standard model Higgs boson discovery, so it fits even better. So there are many precise predictions, which are verified by the experiment over many order of magnitude. So this is one of the, at the 8 TeV, the LSC prediction with the theory and the experiment list. But this standard model has a very serious drawbacks. So this led us to motivate to look for the beyond to standard model physics. At LSC, and LSC is the best place due to its the highest accelerator on the Earth. So the past 2 years have been very exciting, and with the context of the search of the beyond to standard model, so we know that the standard model Higgs is discovered, but there's no sign of supersymmetry yet. And therefore, the exotic searches have never been more relevant. And we are, at LSC, we are exploring the electroweak scale at this moment. So I will focus on the selection of those beyond to standard model searches from both the experiments, the Atlas and the CMS. So since there are lots of the channels and the results, so I would be just focusing on the latest results based on the ATV data. So it's not possible for me to show all. So if you want to have a look, so you can click over this results. Just to give the heads up, so we have a very long list of models lying over there, and on the right-hand side, you can see a long list of the signatures. And if one particular model has more than one signatures, and for experimentalists, it's a very complex two-dimensional problem. So one has to take this practical signal approach and go with the less model dependent. But it's very important to seek as many signatures as possible. So before I start, I just want to look like how do we work, like so the search strategy. So we look at the interesting signal. So it's possibly based on the model of interest. Example, the simplified models like 2000 originating from the SUSY model with S-taus. And then find the case where the Bayesian standard model is dominant over the Monte Carlo background. So we go for the requirement of the kinematics requirement, the event passing this kinematic requirement, and then look for the resonance in the object distribution, like in Riemann. This is like a typical gamma jet resonance plot here. So it describes that the data over the background and data fitted, and the Q star model is lying over here for description. And then we look for the discrepancy, and if we didn't get, and then we set the limits on the Bayesian standard model up to 95% confidence limit. So before we go, we have to understand the background also. It's very important. So the background comes mostly from the standard model. So there are two types of backgrounds: the irreducible or the semi-data driven, where the normalization is done in the dedicated control region enriched in the specific background, example, the top pair production. But one has to compromise the closeness to the signal region, stats and handling of percentage here. The another is the reducible or the data-driven backgrounds, so like the jet smearing for the multi-jets or Z plus jet background, and the matrix method for the background from misidentified leptons. So once we get the background, then we test the background in the validation region. So we define the target-specific background process and without exposing the data in the signal region. So this is one of the signal region, validation region where we have validate the background with the data. So to start with the search for the supersymmetry. So Bayesian standard model is supersymmetry and exotic physics. So I would be talking about the both, giving the results on the both. So this is again the famous plot which was shown in this conference many times. So this gives the inclusive cross section of the supersymmetry at the ATV at the LSC. So, and we know that there are three categories of the particles. So the strong production of the gluons, so the first or second generation S quarks has because the LHC is a proton hadron collider, so it has the tightest limits for the particle which is interacted with a strong way. So its expected sensitivity we have is up to right now is 1.2 TeV. It's followed by the strong production of the third generation S quarks, S top and S bottom. So it is expected sensitivity of up to 0.7 TeV. And on the lower side of the graph, there's electroweak production of the electrovenions, which are GNOs, neutrinos, and leptons, where expected sensitivity is up to 0.2 to 0.5 TeV. Here is the long list of the models which Atlas and, of course, the CMS also have searched around. And there's a long landscape of the models and with the mass limit threshold. So it's not possible for me to discuss everything. So I will just discuss briefly the few of the newer models or newer results from all the three categories, the strong, third generation, electroweak. So the first category is the strong production. This is the production of first and second generation S quarks and gluons, which is motivated by supersymmetry models that involve the strong production processes and cascade of decay of new particles. So as LSE provides the tightest limits, and one looks, Atlas and CMS both looks for the highly enriched signatures consist of multi-jets and the missing ET. So I would be talking there. This is just a recent results. There are a lot of more, but I would be talking about the two results one from Atlas and one from CMS. So first is the SQuark GlueNO searches. So in case of Atlas, it searched for the SQL gluons through the three main processes. One is the direct S-bottom process, where the S-bottoms are produced in pair and then decays into neutrino with here the Higgs. And here the Higgs is assumed to be the same as the standard models of 125 GeV, decaying into the BB bar. So in the this model is highly sensitive to the Higgs going to the BB bar. And so in the end, we get the 6 B jets and the missing ET. The second model is the GlueNO S-bottom model, where the GlueNOs are produced in pairs, and it decays exclusively into the S-bottom pair because all the other quarks, heavy quark, they are assumed to be heavy. So it decays exclusively into the S-bottom. And then in the end, we get the 4 BGBs and the 2 and the missing ET. And then the third one is the GlueNO S-top, where again there's the GlueNO pair production, which decays into the S-bottom. And then in the end, we have 4 top quarks and the missing ET. So these two models depends upon, they are highly sensitive to the GlueNO S-bottom production. So Atlas selects the event with 0 or at least 1 isolated leptons, and with the multi-jets with at least 3 bottom jets. And kinematic variables are required. They are the scene combining the missing ET, jet transverse momentum, lepton transverse momentum, and more. And after the event selection, so events are classified into 9 signal regions for sensitivity to the kinematic. This is one of the example of one of the signal region, where it consists of 0 lepton, 7 jets. And this is a plot from the missing ET distribution of the data over the plotted over the background. And the 2 signal regions are also the overlaid over here. So this is after all the requirement, except the requirement as shown by arrow. So no excess has been observed here in the Atlas search. The same similar kind of, but complementary search, the CMS look for the events with greater than at least 3 leptons, which are very rare in the standard model. So it's considered many cases with the sign and the flavor of the lepton pairs. The irreducible background is from the WZ and ZZ. So it uses the lepton isolation requirement, and missing ET and the jet transverse momentum are the 2 variables which were seen to look for the signal over the background. And this is one of the example of the missing ET over in the WZ and reach control samples. So this is the data, and here the misidentified is mostly the background from the Drellian here. So CMS also interpret the 3rd generation SUSY and rear flavoring while letting decays tau to Chambers and Higgs. So here is the summary of the SQuarks and the GlueNO. So a lot of complementary analysis between these two, and here I'm just showing that one of the limit plot the CMS has put on the S-lepton and next to lightest supersymmetric particles, GMSB model. Here actually the finding is here. So you can see that this scenario is where the right-handed mass degenerate leptons, they are considered to be the next to lightest supersymmetric particles. So this is the plot between the GlueNO mass and the Chagino mass, the limit plot, and this is the observed limit and the solid line, and the dashed line is the expected limit. And one can see that in case of the strong partner, super partner production, so this limit exponentially goes to the horizontal side, and for the weak super partner, it goes to the vertical side. So here also the atlas has the plot from the atlas, so the GBB off-shell model, which I described just back. So here is the plot between the gluino and the LSP mass, and with the 0 lepton and 3 B jets channel. So the plot inside the contour. So this is the observed and the expected limit. So inside the contour is excluded now. So regarding the top two charm Higgs results, which is a flavor, as discussed, I think, many times here in this conference too. So this is the CMS results for where the proton is decaying into TT bar, and one top is decaying into bottom W, and another one to the charm Higgs. So, and the Higgs is assumed to be like decays into the 3 cases, Higgs to WW, tau tau, and ZZ with this branching ratio. And the limit on the branching ratio is come out to be 1.28% over here. So another such is gluino production with the off-shell S-stops from both the collaboration. So the gluino can decay via virtual S-stop if the mass of the S-stop is greater than mass of the gluinos. So the final states are with the 4 top quarks and the 2 neutrinos, and lead to exclusion in the gluon neutrino mass plane. So this is the summary, the recent summary of the just from the CMS and the Atlas. So both are similar to the things, only that one can see that the Atlas has reached up to 1.4 TeV at this moment. And yeah, so the next is the 3rd generation and the direct production of the S-top and S-bottoms, so which has produced, actually the S-top and S-bottom can be pair produced or via the gluino fusion. So they are extremely rich final states and include the leptons, multiple jets, and some of them are B jets and missing ET. So here the recent results from the Atlas and the CMS look for various scenarios, and I would be presenting the two results over here. So this is 3rd generation, the direct production of the S-stops. So, here the S-stops has been, this is the phase diagram for the S-stop mass with the LSP mass. So it depends upon the S-stop mass and the LSP mass. So there are few criteria one can consider about it. So the best is, the highest was like, if the difference between the mass of S-stop and the LSP is greater than the mass of the tau is very high, then the S-stop is decaying on shell to tau and the neutrino. And if it's not greater than the mass of S-top, mass of the top, but it is greater than the combined mass of the B's and the W, so it decays, the stop decays off shell. And further, if you go down, if the stop is further light, then it decays into the B's and the 2 distinct fermions. And if the mass of the S-top and the LSP neutrino is almost the same, then it decays into the charm and the neutrino. And further, it's not allowed kinematically. So this is, as described here, all the 3 scenarios. So one can say that it targets, the Atlas search targets the 2 body decay and S-top decay, 3 body decay, and 4 body decay. So, and Atlas uses both the cut and count shape methods to search for the deviation from the standard model. And to enhance the sensitivity, so the various variable target the different kinematical regions, so the transverse momentum combination, soft leptons for low mass S-top, and compressed scenarios, and R-jet. So this is one of the example, one of the kinematic variables, the missing ET, and the signal, and the data over the background. So here in case the most significant background is TT bar and the W's also. So nothing has been, so the data is exactly at the background, so no excess has been observed. On the other hand, the CMS, actually it searches for the supersymmetry through the direct production of the S-stops with the Higgs and Z boson in the decay channels. So it targets actually the heavier stop. So it considers the events with 1 lepton, 2 lepton, or greater than 3 leptons, and the multiple jets, out of which at least there are 1 or the 3 B jets. So, so this is one of the scenario where B jet multiplicity of one of the case where the final states are 3 leptons and no Z here. So this is the data and the background, and so the main here the background is a non-prompt lepton. So we can get the 2 leptons and 2 prompt lepton and 1 from heavy quark or something misidentified as. So it can be like 3 leptons, non-prompt leptons. So CMS target the S-top2 to the S-top1 production. So and here is the plot showing the mass plane between S-top2 and S-top1. So, and we can see here the limit plot. So the highest sensitivity is, this is the green one. So the highest sensitivity is for the case where we have a 3 lepton and the no Z. But there are other scenarios, 1 lepton and 2 leptons. The blue one and the orange one, we can see that it has not a bad sensitivity, it's a good sensitivity here also. So all the 3 cases has been used, and one can see that the combination, if we combine all the 3 cases, so the sensitivity reduces to like 10 to 15%. It's not much. So the analysis is the split by the number of the leptons and the B jets, and again the many kinematic variables for the background suppression like missing ET, transverse momentum. So in total, because there are many conditions and scenarios, so in total 96 signal regions have been, the signal has been looked on, and so the limits in also the limit plot in S-top1 to S-top2 mass plane, but it indirectly also probes the region of the S-top mass plane. So here is the summary of the 3rd generation S-top. So as this was shown many times here also in the conference, one can see that this is a summary plot 2004 from the Atlas. And it consists of all the possible scenarios over here, the 2-body decay, 3-body decay. This is a 4-body decay. As we can see that most of the phase space actually is shrinking. So we're not left with much space over here. So there's only a few spaces over here, but one can see that this one space here where the stop mass is equivalent to the top mass constraint. Top mass is constrained by the recent TT bar cross-section measurement. So this is the signal strength of one of the paper published by the Atlas, so where the signal strength has been performed over the mass of S-top and excluded the region between the S-top and 177. So this area is also shrinking now. And regarding the similar plot is from the CMS. The only thing is that the CMS also, that's as described before, also that targeted indirectly the S-top to S-top1 search over here. And this is again the mass plane between S-top2 and S-top1. And all the 3 categories have been defined where the decay S-top2 to S-top1 via Z or via the Higgs boson. So, and these are plotted with the branching ratio of the Z boson. So one can see that higher sensitivity is through when the S-top is going to S-top1 via the Z boson. And the least sensitivity is from the Higgs boson here. So, and this kinematic region is also already excluded because if the mass of between the S-top and S-top and the LSP is less than the mass of the Higgs. So there is another summary I can want to add this. This Atlas has recent results on the spin correlation in the TT bar. So it's based on the opposite dilepton channel. And so that the delta phi between like the two leptons is used to exactly the correlation between T and T bar spin. So this was actually described in one of the parallel session. And I'm just giving the overview of that. So this is the limit plot of the mass of S stop and with the cross section to the branching ratio. So one can exclude the mass of S top between the mass of top and 181 GeV. So the third category is the electroweak production, which is a search for the neutrinos, charginos, and S leptons, and I will talk about a little bit about R parity correlation. So this electroweak production is a very smaller cross section. So, but we have a tighter limit for the S quark, first generation S quarks and gluinos. So this area has received a lot of attention now from the LSC. And the cross-section is very small, but it's a cross-section for electrovenous around 300 to 400 GeV is equivalent to the cross-section of the first generation S quarks and the gluons around 1 to 1.5 TeV. So the main signature here is the isolated lepton and the missing ATN. So these are the Atlas and CMSs, quite a variety of the final states, and I would be talking about the 3 states. So first, from the Atlas results, so Atlas targets the direct S-tau production and the chargino neutrino and chargino decay through the S-tau. So this is how the one is the direct S-tau production, and this is the chargino neutrino and the chargino decays. And so it looks for the final signature of the 2 taus and the missing AT. So this is one of the signal region. In particular, the Atlas has performed the search in the 4 signal regions. So the first 2 signal regions are targeting the direct S-tau production, and these 2 target the chargino neutrino and chargino. And this is one of the signal region which targets the chargino neutrino production. So where the mass of effective mass has been plotted of the signal in the background here, and with all the requirements except that the requirement which is shown in here, in the arrow here. So nothing excess has been found. So and the limit has been plotted on the mass of chargino and the mass of neutrino production, and the Atlas has performed that on the simplified model, and so this is the observed and expected limit over here, and this region is excluded by the left here. So the limits on the chargino mass is 345 GeV with the chargino pair production. The CMS, on the other hand, it searches for the chargino neutrinos, just neutrinos and S lepton signature with the leptons, WZ and the Higgs, as described over here. And so it targets 1 or 3 or 4 leptons and the missing ET. So this is one of the signal region defined by the limits of the mass of the dileptons and the mass of, this is actually the events, all the events are split by the number of leptons in the bin signal region here. So out of the 3 leptons, this is the mass of the 2 leptons here, and mass of the, so one lepton targets chargino neutrino via the WH, and the 2 lepton targets direct S lepton production. 3 leptons target chargino neutrino through S lepton, and 4 leptons interpreted in the Gauge-mediated symmetry breaking. So these results actually they probe the charginos and neutrinos with mass up to 720 GeV, and S leptons up to 260 depending upon the model. So this is the electroweak summary. So both the analyses covered the wide variety of the possible decays of the neutrino. So this is the CMS one, and Atlas has performed over a wide variety of the final states. But the most of, if you go by the shape, so the limit plot is almost similar to one, except here the CMS has the sensitivity here for the low sensitivity is from because it's, CMS performed the search of the 3 leptons, so decays by WZ, and one can see that the expected limit is better than the observed because there's an underproduction in the 3 lepton analysis here. So this the limits plots, it depends upon the final states. As we can see, there are lots of final states. So it's weaker for the tau leptons, and the probes chargino neutrino mass up to 700 GeV, and Higgsino mass are probed up to 210 GeV, but 380 GeV is in the GMSB model. So there is before that, I was talking about the R parity, all the signature where the R parity was conserved, but there's another search by CMS and Atlas where the R parity was violated here. So if the R parity is +1 is for the standard model, and for the -1 is for the supersymmetry. So the product of the least supersymmetric particle, it depends upon the lambda coupling here. So this is the RPV superpotential model. So this is the first 2 terms violates the lepton conservation, and the third term violates the baryon conservation. And this lambda is the coupling constant, so, and IJK is the generations. And so from the Atlas point of view, so it started the search with the 4 leptons and missing ET. So this is a very versatile analysis, interpreted in electroweak, gauge-mediated, and R parity violating. So it's a very low background, so 9 signal region contains 0, 1, or 2 taus. So this is a limit plot, and next to light supersymmetric simplified model, the mass of neutrino and the BINOs here. So, and the various colors depends upon the coupling constant. So there are many cases here, and one can say that the maximum sensitivity is when they decays into the electrons and the muons, and the limits are weaker for the decays of the taus. And also this is events before this, the mass of the neutrinos, when the mass of the BINOs, if this is less, so no events are generated over here. So the limit plot on the Gluino, limits on the Gluino is 1.35, and the limits on the Chargino is 750. On the other hand, the CMS looked into the 3 leptons in final state, so discovered both the terms, lambda and lambda star prime, and there is 8 signal regions target the R parity violating stop decay, and some of the decays, including the B jets, are binned in ST. So because here in case of R parity violation, so the least supersymmetric, lighter supersymmetric is it decays and it's no longer stable. So missing ET cannot be used here. So the ST variables is used here. So it is just some sum of the missing ET and the missing ET of the jets and the leptons. So this is the exclusion region from the CMS, the plot between the stop and the BINOs here. So the signal to the left is excluded here. So instead of the SUSY, in addition to SUSY, so there are many other exotic searches also. So I would be talking about some of the results from the exotics too. So the resonances, dark matter, vector like quarks or something. So the first is look for the heavy resonances, which is the dilepton channel here. So this is predicted by the heavy gauge bosons, the Z prime, W prime, which is grand unified theory, and RS extra dimensions here. The experimental challenge over here is that we have to understand the detector performance in the control region, and important also to discuss just the Monte Carlo simulation. In case of the dilepton, so Z prime to do E, so we just plot we take the 2 high PT leptons that are prompt and well isolated, and reconstruct the invariant mass here. So this is a plot from the atlas and the CMS. The invariant mass of the dilepton, the signal, the data over the background. So the main background here is Drelian, and so this is the two signal models are overlaid here. And this is a bin-to-bin correlation between the data and the Monte Carlos here. So nothing excess has been found. And so this is one of the dielectron event observed in the ATLAS experiment where the combined mass is 1.5 TeV. So both the collaboration has put a limit on the CMS and the ATLAS. They put a limit on the Z prime, and which has the same coupling as the standard model Z, the spin 1, and RSKK graviton with the spin 2 here. So this is the newest results from the ATLAS and the CMS of the mass of the limit plot from the mass of Z prime, and the signal and the cross-section to branching ratio. So ATLAS has considered many Z prime models, like say SSM, and the other like is the chi and the neutrino. And there's one more, the excited boson also here. And the CMS, but that there is care must be taken actually when if you interpret the CMS results with the ATLAS, because CMS sets the results on the narrow Z prime, but the ATLAS sets a limit on the Z prime with the width and the coupling of the Z prime here. So the coupling are just shown in the bracket here. So the next is to search for the heavy resonances in the dijet, where we take the two highest PT jets and construct the invariant mass and look for the new physics over here. So this is one, the plot between, this is ATLAS and CMS, the reconstructed mass of the dijet, and it's overlaid over, the data is overlaid over the fitted background, which comes from the phenomenological fit of the data given by this function. So this function describes the multi-jet backgrounds quite well. So both, there are some differences between the two analyses, so that because the ATLAS used a combination of pre-scaled jet triggers, while the CMS used the HT and the MZJ combination at the high-level triggers here. And while the ATLAS used the anti-KT algorithm for the jets with 0.6 radius, while the CMS used with a wider radius over here. So, and both experiments use the cut delta, like it's a rapidity difference between the two leading jets and the MJJ. So this is the dijet event, typical dijet event. One can see that the jets going into depositing energy in the calorimeter. So this is again nothing excessive in pound. So the ATLAS has put a very stringent limit on the excited quarks, and of many other models like W prime and W star and black holes. The CMS also have performed a variety of the search signals over here. So one can look at the sensitivity is increasing now quite a lot for this channel. So another search is the dark matter at LHC. So we, as discussed, the dark matter has no interactions beyond the gravity. So what if it couples to standard model particles very weakly? So it could be through the weak force. So if the dark matter is weakly interacting massive particles, so it could be produced at the LHC, and however, the momentum is still conserved, so momentum imbalance is countered by missing ET. Large missing ET indicates the presence of the non-interacting particles. How do we detect at the LHC? So we detect something and plus missing ET, and this, because we need to trigger something, we can't calculate just a missing ET. So this something could be a quark or gluon, which is a jet, and then photon and the WZ radiated from the incoming quark. So this is the first search is from the monojet search, where something is from the quark. We have a one jet and then put all the conditions so that there won't be more than one jet, and then we've also vetoed the S lepton. The background is basically the Z plus Z and the blue plus Z here. And so this is the plot from the missing ET, and so the data over the background, so nothing excessive has been found here. And the model considered here is the large extra dimension model by Arkani Ahmed. Here it is like consider that there is a number of extra dimensions which relates of the size R and which relates the fundamental Planck scale to the four-dimensional Planck scale according to this relation. And so this is the limit plot, depends upon the number of extra dimensions and the limit on the fundamental Planck scale here. It's compared the CMS with the Atlas and all the older experimented, and this is the table showing the limits according to the number of extra dimensions here. So this is a typical monojet event here. So one jet depositing energy here. So the next is if you consider the high PT photon and the missing ET. So this is the newest results from the Atlas. And so this all the large extra dimension, dark matter, they predicted a monophoton with the missing ET. And the event selection is the missing ET greater than 150 highest here, as shown here. The missing ET should be greater than 150 GeV. So the plot is the data and all the, again, the backgrounds, and with all the conditions here. So nothing is being, excess being found, so the limit plot has been performed here. So the expected upper limit on the fiducial cross-section is 6.1 at 95% confidence level here. And they also put the limits on the place of parameters of theories of large extra dimension, WIMPs, dark matter, and supersymmetric particles. So I will discuss this again later here, but this is just to show that monophoton event here. And then the interpretation of the dark matter. So we didn't get any excess, so we compare the sensitivity with the existing direct and the indirect searches. So in the case of model independent search, so the chi is only particle in the LHC reach, and the standard model chi mediators are very heavy. So, and one can look for the two operators, the D5 and the D8, the spin independent and the spin dependent operator here. So this is the summary plot from the dark matter. So limits on the WIMP nucleon cross section over the mass of the chi. So this one can see that for the in case of spin independent, so the CMS monojet has a maximum the sensitivity over all the mass range of M chi, while in case of spin dependent, it already crossed all the sensitivity from the another indirect and direct experiment. So this is the mono WZ operator, which has the maximum sensitivity over here from all the mass region. So the next one is the exotic heavy quark, so which is motivated by the little Higgs model and the model with extra dimensions. So this is existence of the fermionic partners of the top and bottom quarks. So this is a variable, also the variable alternative to solve the hierarchy problem. So as discussed here before my talk, it was discussed that it leads to reactivity symmetry breaking, and it cancels the loop contribution from the top quark to the Higgs boson mass. So the mass should be at or below the TeV scale. So there is a constraint from the discovery of the Higgs boson. So the fourth generation and the quarks are disfavored because they enhance the Higgs to tau tau and suppress the Higgs to gamma gamma. But there's the other type like vector-like quarks, so like the left and the right-hand chirality transform in the same fashion, and the mass of the independent from the Higgs boson coupling, and there's no constraint over here from the Higgs discovery. There's another character, is a quarks with exotic charges, with just a top partner. So it doesn't contribute to the Higgs cross-section, and almost no constraint from the Higgs discovery here. So this is the recent results from the Atlas. the vector-like quarks, the heavy quark top and bottom decays into the Z and the top and Z and the bottom. So there's no assumption of the top and the bottom branching ratio. So, and they plotted the invariant mass of the Z and the highest PT B jet. So this is mass of ZB. It's used as a final discriminant in the dilepton channel here. So, and in case of one B tag, in case of B, heavy bottom, so it's strongly peaked at the heavy quark mass and this MZB distribution. And in case of lower, in case of 2B tags, which is in case of a heavy top, so it peaks at the lower value and it's wider also. And this is a limit plot from both the scenarios as a function of mass of heavy quark with the cross-section plot, and the limits have been put on SU2 vector doublet. So top quark, heavy top as 735 and heavy bottom as 755 GeV. So Atlas also performed instead of, that was a pair production of the top quarks, but this is a singly, also considered the singly produced heavy top quark as performed, as described over here. So this is also a very important analysis. So the dominant mode of, because it is a dominant mode of production at the higher masses. And it probes the electro-weak coupling, the mixing with the standard model quarks. So here the analysis uses the event with high PT Z bosons decayed into leptons with B jets. And the requirement is the extra jet activity optimized to search for singly produced vector-like quarks. And so limits are used to assess here the constraint on the electro-weak coupling parameter of the new quark. So these are the limit plot for the singly produced top and the bottom, and with this cross-section times the branching ratio of the Z. Yeah. Oops. Okay. So on the other hand, the CMS has performed the search on the top Higgs resonance here, where the heavy tops decays into top, and the Higgs and Higgs is decays into exclusively to BB bar. So because previously many searches has been performed with the Higgs to the lepton channel, but this is the first time analysis performed with this purely hadronic final states here. So this is predicted by the various models like extra dimension composite Higgs area. So this is a very highly boosted topology. So when after getting the boost, all the particles, they are aligned to the same direction as the jet, and it's very difficult to separate and to tag that. So they use the top and the Higgs tagging techniques over here. Hello, yeah. So